Well, happy Tuesday evening. Hey, it's Thanksgiving week, and I'm thankful for you tuning in to this amateur radio upgrade class. For those who might already have their general class or advanced class license in the United States, the whole purpose of this class is to help you attain the amateur extra, the pinnacle. We use this book, the American Radio Relay League Extra Class License Manual. Hold it straight, Gary. 13th edition. So if you'd like to play along at home, all of our previous classes have been recorded and are up on YouTube, on my YouTube channel, which is cleverly named W4EEY, my call sign. And if you'd like to go back and you can catch up and get your amateur extra class license, and you get additional frequency privileges and also the bragging rights to say that you're an extra. So Gary is my name, if I didn't say it already, and tonight we're going to conclude chapter 9 in the book, which deals with antennas and feed lines. And so here's our class schedule tonight, the 25th of November. That's chapter 9. Then next week, Dave will be up covering chapter 10, topics in radio propagation. Then the following week, chapter 11, the last chapter in the book, safety. And then after the intermission on that night, we'll take a practice test, a 50-question practice test together and see how we're doing. And then on the 16th of December, we'll come back to take 2 additional practice tests together, and that will be our very last class. So after tonight, there's only 3 more classes to go. If you haven't already, I want you to please find and schedule a test session to go take your amateur extra exam, the 50-question multiple choice test. And here's a couple of resources for you from the ARRL, the URL on top, and then from hamstudy.org/sessions there on the bottom. So the finish line is ahead. Hang in there. We're almost there. So come back to me just for a second, Bruce. Many people come to our class not having taken our technician class or our general class, which is fine. That's perfect. That's great. But sometimes, at least I do, I assume that you might know something. And then I got some questions last time we did this class from some students. And so, okay, this is going to be review, but there were enough questions that I thought, well, maybe I should cover this just to make sure that we are all on the same page. So you might remember the frequency pyramid, which talks about the relationship between frequency in megahertz and wavelength in meters. Let me turn on my laser pointer here. So here we have the frequency pyramid. Speed here is the speed of light. Frequency in megahertz, wavelength in meters, and it gives us these formulas here, that frequency is equal to 300 divided by the wavelength in meters. If you're trying to, you know the wavelength and you're trying to find the frequency, or vice versa, if you're trying to find the wavelength, that's 300 divided by the frequency in megahertz. They are inversely proportional, and that 300 comes from 300 million meters per second, which is the speed of light and also the speed of radio waves. So here's another recasting of the pyramid, 300 over the frequency in megahertz, and then you can find the wavelength, or 300 divided by the wavelength, and you can find the frequency. This is handy if you're trying to find lengths, for example, for antennas. If you're trying to build a half-wave dipole antenna, well, this will tell you the full wavelength, and then you divide that by 2, and then you get to the half wavelength. All right, I don't want to insult you, but this was an actual question from a previous student. He said, Gary, I don't understand the difference between a closed circuit, an open circuit, and a short circuit. Okay, so closed circuit, is an operating circuit that you see here with a power source and a load. An open circuit is when we have an open in that connection. And this load here, we're showing a light bulb, but this could be a transmitter, and this could be an antenna. So that's a good working circuit. This would not be a good working circuit. This would be an open transmission line, maybe going to an antenna. And the same token, a short circuit is a connection between two wires that maybe shouldn't be there. So if we were looking at the end of a transmission line, let's go over to the calculator camera just for a second, Bruce, if you would. So here is a transmission line that I've cleverly prepared. This is an open circuit. You see the shield there and the center conductor are not touching. This would be a short circuit where we've actually connected the shield, stop moving, to the center conductor there. And so this would be a short at the end. So when I talk about transmission lines with a short at the end or an open at the end, that's what we're talking about. All right, we're all on the same page. Let's go ahead and get started and talk about some antenna systems, section 9.3. Students find the most interesting things. I think Dave will agree. So I copied this diagram of a transmission system from a British website. And it says everything, the point I want to make is that everything from the transmitter's RF output to the antenna is part of the transmission system. And I didn't really even read the thing that's highlighted here in yellow, and then I got a question about it. Why do you say this? Oh, I didn't say that, they said that. But it has to do with grounds and grounding, which is a huge subject, but we'll talk more about it in the safety chapter, because there are different roles that grounds play. So don't worry about that if that confuses you. That's not the point of this slide. The point of this slide is that after the transmitter, you may have a filter, you may have a standing wave ratio meter, you may have an antenna coupler or tuner, antenna switch, anything. That's all part of a transmission system. And we want all those parts of the transmission system to be of a common impedance, because when we do that, we get the maximum transfer of power from point to point, unit to unit. Impedance matching minimizes losses. And there are different ways that you can do this. Impedance matching can be done using a radio frequency transformer, like you see up on the top. Now this is more for receiving, but RF transformer. It can be an L network consisting of an inductor and a capacitor, kind of making an L shape here. Can also be a quarter wavelength long transmission line transformer. We're going to talk more about one of these here coming up. And the whole point of it is to get a matched impedance. So look at this pulse traveling from left to right, and it all is being absorbed by the load on the right. That's the purpose of this slide, is just to, this would be a matched impedance. No reflected power coming back from the load. This would be a standing wave ratio of 1 to 1. Yeah, that's what we're hoping for. This is not. This is 100% reflected power, where the energy is coming from the transmitter going to the load, but it's being totally rejected. This is because there's an open circuit and the far end. It's not even connected to the load. I know that because it's coming back at full strength and at the same polarity. What you're likely to see in your station is something like this, a partial reflection of energy, where the majority of the energy is being absorbed by your antenna, by your load, but some of it is coming back. Notice it came back in a different polarity. It's going down instead of going up. That happens when you hit a lower impedance than the transmission line. So something below 50 ohms, you'll get this inversion of polarity of the reflected wave. So here's the absolute worst, an open circuit up on top. You saw that with the coaxial cable. Short circuit there on the bottom where all the power is coming back, but it's changing in polarity. So what happens when you have reflected power? Well, we know then that the standing wave ratio is not 1 to 1. It's worse than that. And I want to show you, this is a standing wave. You may not have seen one. If you look closely, the blue line that is going from left to right, the wave that is going from left to right is going toward the load, and the red is coming back from the load. That's reflected power going back toward the source. And where they algebraically add together, you get this black wave that is going up and down in concert with the summing of those two waves. It's not moving on the transmission line, it's standing on the transmission line, and this is a standing wave. So if we're talking about voltage here, then that would be a voltage peak here, positive and negative, and here, positive and negative. That's a voltage standing wave. So you're seeing a standing wave as the result of reflected power. So again, not to overemphasize, but why do we do impedance matching? Well, to minimize losses and to get the maximum transfer of power. Oh, we already went back to basics earlier tonight. Well, now we're going to learn our ABCs. Well, not quite. we're going to go Greek. So I used to work at a university. It's now a university. It was just a community college then. It was called Delta College up in Michigan. And this is the Greek symbol delta, which means a change in or a small change in. If we take this delta and we turn it upside down for the convenience of our diagram, this is what we call a delta match. And a delta match for an antenna is in this case, it's a 600 ohm line. And this is designed to connect a high impedance feed line, 600 ohms, to a low impedance antenna. And so it comes in, and then you have a distance of line going off to the side. This is a half-wave dipole, for example, and it's connected together. It's not broken in the middle, but you can feed it using this delta match. It's connected to 2 points slightly off center. So delta match is used as a balanced impedance converter from high impedance feed lines to low impedance antennas. Here's another look at it. Oh, if you saw the dimensions over here, this is in English units, inches and feet, or feet actually there. Here's the metric equivalent for, again, a delta-fed dipole antenna. Here we're using a 300 ohm twin lead feed line, but it'll work. So you can use this if you have back in your ham shack an antenna coupler that might have a balanced output with a 4-to-1 transformer. You could use the 600 ohm or the 300 ohm line and feed your antenna. And the 300 ohm and the 400, 600 ohm lines have very low loss, and that's one thing. So they're really good for long transmission runs. All right, so that was the delta. Here we have the gamma, okay? So a gamma match is another means of doing impedance matching in order to get the maximum transfer of power. It's unbalanced to balanced. So in this case, a half-wave dipole antenna is a balanced antenna. It's got one pole over here and one pole over there. What we do is we feed it here with coaxial cable with the ground connected right at the very center of the antenna, and the interconductor is connected through a capacitor and then through a line that goes over and couples into the antenna. This is inductance here, so we have a capacitance and inductance, and it steps up the impedance. And you still have a grounded driven element, and the capacitance, here's a schematic of it, it cancels the inductance of this matching network. So this is called a gamma match. And you'll see it used on Yagis and other systems as well. Gamma matches are also used if you have a big tower and you'd like to turn the tower into your antenna, maybe for 160 meters or for 80 meters. This is a form of the gamma match. So you can see the schematic is the same. You come in with the coax. You have a gamma capacitor here. You have a gamma line that goes up to a point on the tower, and then it connects over and it feeds RF energy into the tower. We're not going to go into detail on how to do that, but I have provided you here with a link to an excellent YouTube video that will tell you how to feed your tower using a gamma match. More Greek, now on to omega. And the omega match is very similar to the gamma match in that it adds an L network ahead to provide additional matching for low impedance antennas. So that's what you just need to know about the omega match. So here's a comparison: the delta up on top, the gamma match there down on the bottom, and a T match, which is kind of like a double gamma, and then the omega match here, which has this additional capacitor L network at the beginning. So impedance matching, these are all techniques that amateur radio operators use. Another technique that can be used is stub matching, and that's by adding an open or shorted transmission line at a specific point on a transmission line, and it will provide an optimum match at one frequency. So, here's our transmission line. In this case, it's open wire line, and by adding just these additional lines here, it could be shorted or it could be open, you will actually improve the impedance match of the antenna. Well, how am I going to know how to do that? The Smith chart can help you with that, and we'll be talking about the Smith chart coming up. In fact, you are going to be inducted into a secret society just a little bit later. Shh, don't talk about it. Okay. VHF, UHF, did you know this? If you put up a dipole antenna but you don't know how to match it or the best way to match it, you can actually run the transmission line to it, and then if you have a stub below the antenna, and just by moving this feed point up and down on the stub, you'll see on a VSWR meter, you'll see that the reflected power goes down. So you can use stub matching. This is known as universal stub matching. Very practical at VHF and UHF because the length of the stub is not very long. All right, Yagi antennas. We talked about the gamma match already. That's a grounded driven element. You have a direct connection to the boom, and the boom itself is connected to the driven element. So for static dissipation, things like that, that's good. And you can have something called a hairpin match. In this case, the driven element must be insulated from the boom, from ground. And you can see that on the right, that we have these insulators here. And you can see it's open here in the middle. And this U-shaped thing right here, which is grounded right here, you think, well, that's a short circuit, Gary. That can't work. It's actually at HF, it's an inductance. And it can be as simple as just a piece of wire in a U-shape, as you see here. The way this works is that the driven element of the Yagi antenna, which is normally a half wavelength long, you make it shorter than a half wavelength. Then we say that the antenna is capacitive. And this inductance of the hairpin match cancels that capacitance and brings the Yagi antenna into resonance at the desired operating frequency. So gamma match and hairpin matches are used for Yagi antennas. So amateur radio operators, we use PEP, or peak envelope power, for modulated signals to set our maximum. So 1500 watts PEP maximum, whereas broadcasters use effective radiated power. And when they get a license as a broadcaster, it will say, your FM station has a license for 100,000 watts ERP. It may mean that the transmitter is 30,000 watts and you have an antenna with gain up above that gets you up to the 100,000 watts, because ERP, or effective radiated power, consists of output power, any losses from transmission line, etc., and any antenna gain that gives you effective radiated power. So it's all math. Adding and subtracting math. Transmit power, feed line loss, antenna gain, that will give you your effective radiated power. So I'm going to provide here, this is the formula to calculate power ratio in decibels if you know one power level and another. And this could be used to answer some of the problems we're going to talk about here coming up. but approximation works just as well, and it's much easier, so don't worry about it. So here is a sample problem. We want to know what is the effective radiated power, and the question is written relative to a dipole of a repeater station with 200 watts output, 4 dB of feed line loss, 3.2 dB of duplexer loss, and 0.8 dB of circulator loss, and finally 10 dBd of antenna gain. All right, so this relative to a dipole is kind of a trick. Don't worry about it. They're talking about a dipole here, and we're talking about a dipole here. Okay, that takes care of that. So now it's just adding numbers up. So we have 200 watts, then we have 4 dB loss, 3.2 dB loss, 0.8 dB loss, and 10 dB gain. When you add them all together, it's actually plus 2 dB of gain. So we started out with 200 watts, so we know that the ERP is going to be higher than 200 watts, so it's going to be more than that. But if we were going to use, and 2 dB is less than 3 dB, 3 dB is twice the power, remember? So twice 200 would be 400. So it's going to be somewhere in between 200 and 400. And here's a table to take a look at. A 1 dB gain is 26% power increase, or 1.26. 3 dB gain, we said, is times 2. 6 dB gain is times 4. And 10 dB gain is times 10. Now, one of our students came up with this great trick. If you know that 1 dB is 1.26, you can find any of these. 1.26 times 1.26 is 1.59, that's 2 dB. 1.26 times 1.26 times 1.26 is 2.01, that's 3 dB, and so on and so forth. Or if you're into powers of 1.26, 1.26 squared is 2 dB, 1.26 to the third power is 3 dB. So you can see the relationships here, 1 dB, 2 dB, 3 dB, 4 dB. Keep this in mind as you're working these problems, because it might be able to help you quickly answer the question. So in our case, 200 watts times 1.58, 1.58, 1.59 gives us 317 watts effective radiated power from the station. That's that transmission system. We're taking into account the transmitter output plus everything else. So we give us a 317 watt ERP. They got more problems like this. Again, we're asked the effective radiated power relative to a dipole. Oh, this is the same problem we just did. Sorry. Here's the next one. So what is the effective radiated power relative to a dipole, again, of a repeater station with 150 watts transmitter power, 2 dB loss, 2.2 dB duplexer loss, 7 dBd antenna gain. Again, dipole, dipole, no problem. We don't have to do any fancy finagling, converting between isotropic or a dipole. What we just need to do is add everything together. So 2 dB feed line loss, 2.2 dB duplexer loss, these should be minuses, and 7 dB gain gives us a total of 2.8 dB gain. That's approximately 3 dB, or approximately twice the power. So it's 150 watts to start. It's going to be very close to 300 watts, and the answer you'll find of the ones that given at 286 watts. All right, here's a question. The effective isotropic radiated power of a repeater station with 200 watts output, 2 dB feed line loss, 2.8 dB duplexer loss, 1.2 dB circulator loss, and 7 dBi antenna gain. Note, they've done us a nice favor here. They've done us a solid. Isotropic and isotropic. Okay, that we don't have to worry about that. So we just add the numbers again, minus 2, minus 2.8, minus 1.2, and then 7 dBi gain, a total of approximately 1 dB gain. Again, it's going to take us up to 200 times 1.26, 252 watts. So that's how you answer these effective radiated power questions. Questions? Oh, let's look at some questions. So what is the ERP, see if you can remember, of a repeater station with 150 watts output, 2 dB feed line loss, 2.2 dB duplexer loss, 7 dBd antenna gain? It was the one we just did. Remember the answer? Delta, yes, 286 watts. And what term describing total radiated power takes into account all gains and losses?
Charlie.
Yep, effective radiated power. And what is the effective radiated power of a repeater station with 200 watts, with a 4 dB feed line loss, 3.2 dB duplexer loss, 0.8 dB circulator loss, and 10 dB gain? Remember, we figured that out. It was a 2 dB gain. So it's it is not delta.
Alpha.
It is alpha, because we start with 200 watts. It's not doubled, so it's not 400 watts. So it's got to be between 200 and 400. So it's 317 watts. I guess that would qualify that one too, but it's 317. All right, what is the effective isotropic radiated power of a repeater station with 200 watts output, 2 dB feed line loss, 2.2 dB duplexer loss, 1.8 and 1.2 dB circulator loss, and 7 dBi antenna gain?
Bravo.
It is Bravo. It was a 1 dB gain, as I recall, so it's a 252 watts. So which matching system for Yagi antennas requires the driven element to be insulated from the boom?
Bravo.
That's the hairpin match, also known as a beta match. And what antenna matching system matches coaxial cable to an antenna by connecting the shield to the center of the antenna and the conductor a fraction of a wavelength to one side?
Alpha.
That is indeed a gamma match. And what matching system uses a short length of transmission line connected in parallel with the feed line at or near the feed point?
Delta.
That's a stub match. You're adding a stub. And what is the purpose of the series capacitor in a gamma match?
Bravo.
It cancels
Delta.
No, it is Bravo. It cancels the unwanted inductive reactance. And what Yagi-driven element feed point impedance is required to use a beta or hairpin matching system?
Alpha.
We first have to make the driven element capacitive, and then we can add an inductance to cancel it and make the match. So it has to be shorter than a half a wavelength. And which of the following is used to shunt feed a grounded tower at its base?
Charlie.
That also is a gamma match. It's a form of gamma match. And which of the following is a common use for a Smith chart?
We haven't gone over it yet.
We will.
Charlie.
Not Charlie.
No.
I told you.
Bravo. Bravo.
I heard it in there. Alpha. It's where you
Gee
can
whizzes.
determine the length and position of an impedance matching stub. You had to take that on faith. Like, I haven't proved it to you yet, but that's the answer there. So, okay, great, excellent. All right, section 9.4, transmission lines. And interestingly enough, I told you broadcasters for the FM world, they use effective radiated power. Broadcasters in the AM world have their license issued, and it's probably specified no more than 10 amps of RF current. And for AM, measuring RF current is a thing. Obviously, more current to a load means more power output. And you can buy RF ammeters, not so common in the amateur radio world, but you'll see them at ham fests. And you used to be able to buy from MFJ. This is the nice one. I thought that was what I was ordering, but I ended up, if we look over on the calculator cam, this is what they sent me. That's not quite as nice. It's from 3 amps down to 300 milliamps, but it's got a ferrite here on the top, and you can run a wire through it, and you can measure current. This might be great for looking at common mode current on a coaxial transmission line. The coax would go in through there, and you could make the measurement, but I've actually never really used it. I was not really impressed with the build quality. But okay, anyway, that's neither here nor there. But just know that for broadcasters, RF current is the specification on the license, and more current means more power. So now, for hams, we don't typically do that. We typically use antenna analyzers because they're very convenient. There is a built-in RF source. You can use them to measure standing wave ratio. You can use them for single frequency measurements or swept frequency measurements. They probably have an interface for a computer. So, for example, here's my Rig Expert AA54. It's got a USB connection on the bottom there so that you can connect to a computer. There's a direct readout of rectangular measurements for impedance, R plus JX, and they're relatively portable. All right. Here's my hand, so it's a pretty good size. What I got when I went to Hamcation down in Florida last year, though, was this little guy. This is Rig Expert's stick analyzer. Now you notice it doesn't have a very big display, so the graph on it is not real great. This guy's claim to fame, though, is that it's very small, very lightweight. Let me take the cover off. You can see there's a SO239 connection there at the top where you can connect it to an antenna or a transmission line. This is so lightweight, though, you can connect it right directly up at the antenna feed point, and this one has Bluetooth. So I can be on the ground on my phone manipulating software that they provide free called AntScope, and I can do antenna measurements up in the air while I'm on the ground. Kind of handy, kind of nice to have. So I just wanted to point out that's antenna analyzers. All of these various features that we have here are possible with the software on your phone or on a laptop or a tablet. Other features, you can use them to measure a cable's velocity factor. We'll talk more about that coming up. You can usually find they have a time domain reflectometer. It's a way of finding out you've got a length of coaxial cable, but you don't know how long it is. We'll connect it up to one end and make a measurement, and you can tell you how long it is. It can also be used to determine the resonant frequency of a circuit by looking at the response of the circuit from the analyzer. I used it to check some bandpass filters in one of my linear amplifiers using the antenna analyzer. So very, very versatile piece of equipment. Now again, you don't want to run your transmitter into this. It'll blow it up. It's got its own RF source, and you're doing antenna and low power testing using this as the source. If you want to measure an antenna's SWR or matching, you can use something like this, a directional power meter. The directional power meter has slugs. That's these things right here. This is a slug. Here's a spare slug being stored on the side. They are for different frequency and power levels. And if you see the arrow here, so on this side it's got what I call the goes in-a, and on the other side it's got something I call the goes out-a. And you feed from your transmitter here, going to the antenna over here. And in this direction, with the arrow pointed that way, you'll measure forward power. If you take this slug and turn it 180 degrees, then you'll be measuring reflected power. And with the two levels known, then you can calculate your standing wave ratio. Although most of the time you just want minimum reflected power. So you can just adjust for minimum reflected power. This is a directional watt meter. Many of them have on the back of the meter a little table where you have these two power values, and it'll help you calculate what the standing wave ratio is. Again, though, pointing out that with a directional watt meter, you're cooking it up between the transmitting device and the antenna. And it must be powered with RF energy from the transmitter in order to get a reading. Whereas the antenna analyzer connects directly to whatever load it is you're testing. In this case, it's a dummy load. So this is a very common, the MFJ 259, one of the still very popular antenna analyzers, and still available from MFJ. My friend Doug just ordered one last week and he got it. MFJ lives. Okay, interesting. All right. Now, if you want to be with the big boys, well, back in the day, professional engineers, if they're using for broadcast and things like that, and they're making antenna measurements for television systems and whatnot, they would use something like this, a network analyzer. And a network analyzer allows you to make measurements, single port and dual port measurements. This one I think is from HP. Tektronix made them as well. And down below is something they call an S parameter test set. That has a goes out and a goes in and it allows you to measure two-port measurements. Well, then oh boy, it's been about 8 years ago now. This came out from a German ham, DJ8SAQ, a vector network analyzer for amateurs. You could characterize components up to about 1.3 gigahertz using a PC for the display, had an internal RF generator and a low noise spectrum analyzer, measured all sorts of different things, including having a Smith chart display. Nowadays, the Nano VNA from China, it was originally designed by a gentleman in the Netherlands, and then of course the Chinese cloned it and made it available at strange prices. And so this version here, it's got different ports, two ports for measurement, and it comes with accessories, some cables and whatnot. The Vector Network Analyzer, also known as the Nano VNA, doesn't really come with a very good instruction manual, so I always recommend this book, Nano VNAs Explained, which comes from the Radio Society of Great Britain. It used to be $10 as a Kindle. It's now up to $18.99. I don't know what happened there. They run out of paper for the Kindle. Oh wait, it doesn't use paper. Anyway, from Nano VNAs Explained, this is a diagram of the Nano VNA with a bridge circuit and mixers. It's actually operating at the audio level, interestingly enough. So you have channel 0 and then channel 1. This is a transmit receive port, and this is just a receive port down here. With any of the vector network analyzers, the Hewlett-Packard, the German one, or this, you have to go through a calibration procedure when you first get started. And you do that by installing an open circuit device. One of these is open circuit, a short circuit device, and a 50 ohm load if you're using it for a 50 ohm system. And there's a calibration procedure that the VNA will have you go through. And I realized I forgot to bring my VNA up from down below. But here's a look at it pictorially. This is for a single port measurement, which you might use for an antenna, for example. Before you make that measurement, you go through the calibration procedure and put in a short circuit, open circuit, and the 50 ohm load, and then you're good to go to make real measurements that are accurate and reliable. Nice thing about this is, see, this is an antenna feeder. Let's say you've got 100 feet of cable going to wherever your antenna is. If you go through this process and put the calibrators on at the end of this feed line, go through the calibration process, Then you connect it up to the antenna. The feed line disappears from the measurement, and you're actually measuring the characteristics of just the antenna itself. So what can a vector network analyzer tell you? Well, it can tell you the input impedance of the device under test. It can tell you the resonant point where the reactance is equal to 0. For amplifiers or other devices, sometimes it can tell you the output impedance. It can also tell you the VSWR, or reflection coefficient. And for filters, you can actually measure in forward and reverse directions. And let's go back down to the workshop where I made a measurement of a bandpass filter that I had in my junk drawer. I want to demonstrate the use of the Nano VNA to measure the output of this filter. It's a trap, and we're going to see if we can determine approximately what frequency range it is. We've already calibrated the VNA using the 3 loads, the open, the short, and a 50 ohm load. And right now we're sweeping between 150 megahertz to about 300 megahertz. And the output of the Nano VNA is on the top. We're going to run that into one side of the filter. And then the other side of the filter we'll bring in down here. If I can get it on there. And there you can see that the response has got a nice definite notch there. Whoops, and if we go over with our marker, we can see that the marker frequency is about 189 megahertz, which pretty much corresponds to what I measured earlier, around 185 to 190. So this is using a Nano VNA to measure a filter response, in this case a notch filter. All right, thank you, Gary, appreciate that. So a VNA can give you information called S parameters. What does this mean? Well, it's called scattering parameters. It comes from optics. And S parameters characterize gain or loss, VSWR, reflection coefficient, and stability for any device under test. The device is treated as a black box, and the VNA gives you information. And S parameters, the numbers after the S indicate the ports that are being used. So here's some various ports. These are single port measurements, and these are 2-port measurements. And 2 that you need to know for the test. Don't necessarily need to know how to do it yet, but a 2-port S parameter test, S21, which was the test that I just did there with the notch filter, has to do with forward gain. How much forward gain is there from the device? In this case, there wasn't any gain, but there was a big notch that we saw there. So S21, forward gain, think football. And then S11 has to do with return loss, also known as reflection coefficient. So S11. That's where you return stuff, is to desk S11. Return loss. It's the same thing as VSWR, and you'll see that here more in a minute. So on the vector network analyzer, we use the top port to measure return loss. You can see it right there written on the VNA. And then the 2 ports, S21, to measure forward gain. And the reflection coefficient has to do with how much of a wave is being reflected, and it can be derived from SWR. If you know the SWR, SWR minus 1 over SWR plus 1 is the reflection coefficient. Well, Gary, what do you mean? Well, engineers use return loss and reflection coefficients, whereas hams tend to use VSWR. So if you want to impress your friends, say I've got a 40 dB return loss on my antenna, which is nearly perfect. And if they know anything, they'll go, wow, he knows what he's talking about. So when you're talking about a mismatched transmission line, you're going to have a reflected signal, and that's reflected in the numbers that make up reflection coefficient. And there is a table, here it is, with return loss in one column, reflection coefficient in another, and SWR in another. So here we have a VSWR of about 17 that has a return loss of only 1 dB. Only 1 dB of power is being absorbed by the load, and the reflection coefficient is here, 0.89, whereas the return loss of 40 dB is really good. Like I said, that's a VSWR of 1.02 to 1, reflection coefficient of 0.01. So just, I want you to know about these terms because we're going to be talking about them. So one of the things that I said that you could do to do impedance matching, we talked about RF transformers, we talked about L networks, and then we talked about quarter wavelength long transmission lines. So in the case here of 50 ohms from our transmitter, we want to match that to a 100 ohm load over here. And what you can do is, if you're, say, operating in the 20 meter band, 14 megahertz, is you can, if you can find cable that has an impedance halfway between the two, between 100 ohms and 50 ohms, well, 75 ohm cable, and if you can measure that out to be a quarter wavelength long, if you do that, you will get an impedance match at that frequency and the band of frequencies. And so this is matching with a quarter wavelength long transmission line. So I needed to do this. I wanted to get additional gain on 6 meters, but where I have my 6 meter antenna, I didn't have a lot of room available. So I had a 2-element Yagi, but I couldn't make a longer Yagi fit. I just didn't have the turning circle in that area. But I could put another 2-element Yagi up above it. Cool. All right. And so that's what I did. And what I did was I used a quarter wavelength long line. Now in this case, with 250 ohm antennas in parallel and resonant with no reactance, it's going to be 25 ohms. So I needed to go between 50 ohms and 25 ohms. So what I needed was a transmission line with a characteristic of impedance of about 37 ohms. So at first I cheated. I bought one from a company called Antennas Amplifiers in Europe. They make combiner splitters, which is essentially just a quarter wavelength long transmission line. I'll show it to you here in just a second. And I used the vector network analyzer to make a measurement. And if you see here where the arrow is there, it's return loss. Remember I said that 40 was perfect? Well, it's 30 dB down. That's near perfect. That's really good. Now, I don't remember what I paid for the commercial unit, but it was more expensive than building it yourself. So I said, well, let me try that. And if you put 2 75 ohm cables in parallel, that gets you to about 37 ohms, and so I built my own. I'm going to show them to you here in just a second. Now, of course, I'm not so perfect. I got to put my glasses on. The return loss on mine is only down 20 dB, so the commercial product was at least another 10 dB better than mine. But Antennas Amplifiers, their device that they used an air dielectric with a velocity factor of about 1. My homebrew unit used RG6 with a polyethylene, which had a velocity factor of 0.66. Hence, their physical links are different while their electrical links are the same. What am I talking about? Come on over here to the demonstration area. So I'm 5'10". This is on the ground right now. This is the antenna amplifier's quarter wavelength long line. It's got one combined port here, and it's got two SO239s on one side and on the other where the antennas run in. I actually have two of these because this is the one I use for field day, where I set up a similar arrangement for field day. So this is very well built, very professionally built. You saw the performance there, very, very good. My homebrew, which of course I had to put DX Engineering stickers on, but I just wanted to prove that I could do it. It has two SO239 connectors on this port right here, F connectors going to RG6 cable, and at the bottom, just a single port. I don't know if I can hold these together. We'll try. But you can see mine is much shorter. It ends right there because of the different velocity factors, air in this one and polyethylene in my homebrew. Let's talk more about velocity factor. Okay, got that up. Let's go over here. So we know that radio waves travel at the speed of light in a vacuum, 300 million meters per second. It travels through bare wire nearly as fast, but it's slowed down somewhat if you use insulated wire. So I get this question all the time is, Gary, can I put up a dipole antenna with insulated wire? The answer is yes. In fact, it might be more weather protected, although UV light might impact it a little bit. But you're going to find that it's going to be shorter in length than if it was just bare copper, because the plastic on the outside has a velocity factor impact. Well, coaxial cable dielectric, that's the white stuff in the middle, causes even more of a slowdown. So velocity factor is how fast a radio wave travels compared to that in a vacuum or the speed of light. And it's expressed as the velocity of the wave divided by the velocity of light in a vacuum. So velocity factor is always going to be 1 or less. And it's determined by the materials used. The denser plastic slows waves down more. So Albert Einstein always said that plastic makes waves slow. Here he is with his radar gun to prove it. So you can buy coaxial cable with a center dielectric of both either foam or solid polyethylene. Foam dielectric has some advantages. Foam dielectric has lower safe operating voltage limits though, but it's lighter in weight. Foam dielectric has lower power loss per unit of length, so you actually get more power at the opposite end. And foam dielectric has a higher velocity factor. Waves travel faster in it than it does with a solid polyethylene dielectric. How can you tell the difference between foam and polyethylene? Use a knife. A knife will easily go through the foam. Piece of cake. You've got to work at it to get through polyethylene. So the velocity factor of polyethylene is 0.66. The velocity factor of foam coaxial cable is 0.8. And there's a table. You can look it up actually if you're buying a commercial cable from Belden or something like that. They'll tell you what the velocity factor is. For open wire line, where air is the dielectric, most of the time it's between 0.95 and 0.99. You can assume it to be 1. Foam, 0.8, and the denser polyethylene, 0.66. So why do we have to know this? Well, there's a question. What is the approximate physical length of a solid polyethylene dielectric coaxial transmission line that is electrically 1/4 wavelength long at 14.1 megahertz? Well, let's see what we can find here. So here's the information, and this is what we need to know. We're going to be operating at 14.1 megahertz, so we need to know the wavelength in meters. Then we need to know a quarter wavelength. Then we need to know the velocity factor of polyethylene, and then we can multiply the velocity factor times the length and give us the actual length of the cable that we need to make. So the wavelength in meters, 300 divided by 14.1, remember the pyramid, that gives us 21.28. A quarter of that is going to be 5.32 meters, and then multiplied by 0.66 gives us 3.51 meters. So that's how you can actually construct a particular length transmission line based on your needs. Here's another one. What is the approximate physical length of a foam polyethylene dielectric coaxial transmission line that is electrically a quarter wavelength long at 7.2 megahertz? So we go back to find the full wavelength, 300 divided by 7.2, 41.67 meters. A quarter of that is going to be 10.42 meters. Foam has got a 0.8 velocity factor, so 10.42 times 0.8 gives us 8.34, so the answer is going to be approximately 8.3. And the last of these problems has to do with air-insulated parallel line, where the velocity factor is very close to 1. You can assume it to be 1. So what is the approximate physical length of an air-insulated parallel conductor transmission line that is electrically a half wavelength long at 14.1 megahertz? So again, here's the full wavelength, 300 divided by 14.1. Half of that, 10.64, and since the velocity factor is 1, then that's the answer, 10.6 meters. Ladder line also has a very low impeding of radio waves, so it has a high velocity factor. And it also has the lowest loss per 100 feet. We talked about that earlier. And it's easy to add stub tuning to ladder line. So these are some advantages of ladder line. So in the email that I sent you last week, I recommended that you go take a look at this video, which is part of the Ham Radio Now series, called Standing Up for Standing Waves. And if you did, it's got a lot of really good, useful information. If you haven't, I urge you to go again and take a look. 2 rules that I want you to remember. A half wavelength line is what we call an impedance repeater. If you have a low impedance on one end of a half wavelength line, it'll measure a low impedance on the opposite end. Whereas a half wavelength, quarter wavelength line is an impedance inverter. If you have a low impedance at one end, you'll have a high impedance at the opposite end. Prove it, Gary. Well, let's consider the case of the half-wave dipole antenna. If you remember, we looked here, we saw this last week with the current distribution on this antenna in blue and the voltage distribution there in red. And we said if you have a high current, low voltage, that's low impedance. And if you have a high voltage, low current, that's a high impedance. So this is a half wavelength long. Each section here is a quarter wavelength long. Notice that's high impedance at the end. It's low impedance at this end. High impedance at this end, low impedance at this end. So that's the proving of the quarter wavelength rule. It's an impedance inverter. Well, what about distances in between that? Well, lengths of coax that are not a quarter or a half wavelength long, or multiples thereof, well, you can have either an open-ended or a shorted-ended. Remember that coax that we looked at the beginning? And when you have this, the links actually behave like reactances. So there's a table in your book on page 9-40. So for open lines, if you have something that is an 1/8 wavelength long, it behaves as a capacitor. If you have a 3/8 wave long, it behaves as an inductor. Really? And for shorted lines, in this case it's reversed. The 1/8 wave is an inductor, and the 3/8 wave is a capacitor. So an 1/8 wavelength open line appearing as a capacitor, think of it as two plates of a capacitor. The 1/8 wavelength shorter line appears as an inductor. Think of it as like a single turn inductor. Why would you want to do this? In an emergency, if you need an emergency capacitor or an emergency inductor, you can make them out of coaxial cable. I have done it, and it works. And I actually, I wanted to see if this would work, so I got out my LCR meter and a length of coax, and well, I made a measurement. So here we are in the workshop with a 1 meter length of RG213 coaxial cable. And here I have an LCR meter, a digital LCR meter. You notice that the ends of the cable, in fact, let's zoom in just a little bit here. I just have them bared out. Whoops, where am I? There we are. So you can see. And I'm going to connect the test leads from the LCR meter to the open coaxial cable. The cable is 1 meter long, RG213. And if we noticed on the LCR meter, we're on the 200 picofarad scale. This open 1 meter length of RG213 has 95 picofarads of capacitance. Well, what happens if we short the other end? Let me just reach up and do that very same thing by wrapping the braid around the center conductor tightly. Notice the capacitance went away. But if we go over to the 200 microhenry scale, we can see now that the cable is exhibiting about 1.3 microhenries of inductance. So a short cable, less than a quarter wavelength long, open is going to act as a capacitor, shorted is going to act as an inductor. So there's a practical example of that. And then to complete the series, a 3/8 wave open line appears as an inductance, and a 3/8 wave shorter line appears as a capacitance. So you can look at that table and puzzle it out, but that's what they're trying to tell you. And indeed, if you need a capacitor, I had to have a capacitor for a loop antenna. And I didn't have one in my junk box that would handle the voltage, so I made one out of coaxial cable, and I was able to get the antenna to resonate. All right, moving on. Resonant circuits. You can have a series resonant circuit where a capacitor and inductor are in series with each other, or you can have a parallel resonant circuit where they are in parallel with each other. And if you think about the current at a particular frequency, at resonance here, remember at resonance, this goes away. This becomes zero reactance, and you're left with just the resistance in the circuit. Whereas in this case, the parallel example here, at parallel they open up, and you're just left with the resistance of the circuit. And if you plot a frequency response of a series resonant circuit with the power going through, or the power going through here, this will only pass current toward the resonant frequency of that device. This will shunt voltage and current except at the resonant frequency of the circuit. So really they have the same power curve at the resonant frequency. They allow power to pass only at that resonant frequency. And impedance, that's what we've talked about in the past in a series circuit. Admittance is something, though, that we talk about in parallel circuits. And we're not going to go too great in depth in this, but I want you to know about this, that for a series circuits, we have impedance consisting of a resistance and a reactance. In parallel circuits, we are very interested in admittance, which consists of conductance and susceptance. The inverse of resistance is conductance. The inverse of reactance is susceptance. All right, hold that thought. Ever seen these before? They're called nomograms, also called alignment charts. This is one for Ohm's law, and you can find it at the URL down here below. And if you know any two of the values, you can use a ruler to find the third. So that's what a nomogram is all about, is using calibrated scales to find out an unknown value. A slide rule, if anybody's ever used a slide rule, is a nomogram of the highest order with various many different scales that once you learn how to use them, you can use them for multiplication, division, all sorts of trig functions, etc. So slide rule is a big nomogram. Well, it is time. Every year when the extra class meets, I bring our students, you've gone through almost all of the course right now. You've absorbed so much knowledge that I am now going to be able to induct you into a very secret society, top secret. Don't tell anybody, but I'm going to introduce you to the mother of all nomograms, the Smith chart. And so to do so, I must put on the sacred garb here and the sacred hat, because I am your grand poobah, and this is the Smith chart, secret society. Don't be too impressed. Okay. Anybody remember Time Tunnel? When I see a Smith chart, I always think of the old TV show Time Tunnel. But Smith charts, what he said was, from the time I could operate a slide rule, I've been interested in the graphical representation of mathematical relationships. And last week we looked briefly again at the Cartesian plane. Remember this? We talked about it. Well, let's look into it a little bit more in depth over at the whiteboard, okay? Yes, it's me, and I still got the hat on. All right, let's take a look here. So here's our Cartesian plane that we talked about before. This is the 0 point here at the middle. The real values for resistance are on the x-axis. Reactance is on the y-axis. Inductive reactance going up, capacitive reactance going down. And remember that we never go over here because we don't have something called a negative resistance. So in reality, this is all we're dealing with, is reactances up above and real numbers on the x-axis. And so this is the zero, whoops, there we go, zero value. This is infinity over here in infinite ohms. Up here, this is the infinite ohms for inductive reactance, X sub L. Down here is the infinite value for X sub C. And so Philip Hagar Smith saw this, and so on here we could plot R plus J something or R minus J something. But he said, look, it's infinite there, infinite there, infinite there. Why don't we combine, and why don't we bend this reactance axis and bring it over here, and let's bend this reactance axis over here. So down here we have anything down below the line is going to be X sub C, capacitive reactance. Anything above is going to be X sub L, inductive reactance. And let's move on. I think I have to exit out of this. Discard. Move on. We end up with this, which is a kind of a simplified version of the Smith chart. But again, 0 ohms over here, infinity over here. This is the X sub L axis. Here's the X sub C axis here, and the real, our R value, here. And we're looking at, these are called resistance circles. Let me just change my color here. So these are resistance circles. Anything that is on this circle is going to have the same R value as down here. Whereas these are, change value again, reactance arcs. Anything that is on this line is going to have the same reactance, in this case X sub L, or down below X sub C reactance. So a Smith chart consists of resistance circles and reactance arcs with an outer reactance axis and the resistance axis toward the center here. Discard that. Move along. So this is what we get the Smith chart that you will see in the book and the more complex ones. It's the same thing. Zero value over here. Infinite over here. Think a time tunnel. We'll get into the infinite. And this chart has a 1 at the center. And most folks, if they're going to use a Smith chart, they're probably working in a 50 ohm system like we have with transmitters. So we would say that this one circle represents 50 ohms resistive, no reactance. Okay? And that's called normalizing. If we say that 1 on the chart equals, well, okay, that's an equal sign, believe it or not. 1 equals 50 ohms. We've normalized this chart. So 0.5 is going to be 25 ohms. 2 is going to be 100 ohms. All right? Just looking, if we say that this is 50 ohms and let's see where I can find the 2 there. Okay. So that's going to be 100 ohms. And this over here, there's the 0.5. This is twice the impedance of this, so this is a 2-to-1 SWR. This is half the impedance of this. It's also a 2-to-1 SWR. And so we can actually draw a circle, and anything inside this circle is going to have a 2-to-1 SWR. So we can use the Smith chart to tell us what our SWR values are going to be. On the outside here are other indices and also a nomogram that can be used for further calculations. And then ultimately we're going to get to this Smith chart, which is both what we just saw with the series circuit with impedance and then the parallel circuit admittance. But don't be freaked out. Let's go back over and let's review. And then after we get through this section, we'll be taking a break. All right, so if we look at a basic Smith chart, it graphically depicts a complex impedance consisting of a resistance and a reactance in series. And one nice thing about the extra class test, it only deals with series, a resistance and a reactance. But I want you to know the rest of the story. The center horizontal line that we looked at here is the resistance axis. Anything value above the line is inductive reactance. Any value below the line is capacitive reactance. As we saw earlier, the outer circle is the reactance axis. It's the y-axis kind of bent back around. The straight line is the resistance axis. And it's made up of constant resistance circles and constant reactance arcs. And one of the scales on the outside is fractions of transmission line electrical wavelength. By knowing that, that's how you can calculate where stubs should be positioned to transform impedances. Again, we're not going to go into details about this, but I just want you to know that exists. So 0 ohms or a short circuit is over here on the left. Infinity is over here on the right. Anything up in here is going to be r plus jx, and anything down below is going to be r minus jx. And these were the resistance circles that we saw here. Everything's going to have a constant resistance. The center of the Smith chart is also known as the prime center. That's where the number 1 is indicated. And these are the reactance arcs. Inductive reactance above the line, capacitive reactance below, all have constant reactance. And normalizing, we talked about setting this 1 value to mean 50 ohms. That's typically what we would do. So if point 1 is 50 ohms resistive, then all of these various points then have this kind of a meaning. This point then becomes 25 ohms of resistance plus J25. Out here it's just plus J50. Here it's J25 minus J25, or 25 minus J25. Down here it's minus J50 in rectangular notation. And as I pointed out earlier too, then the standing wave circles can be drawn so that you can see anything that comes within this circle is within a 2-to-1 standing wave ratio. This is handy on antenna analyzers that can display Smith charts. And again, at the outer ring, one of the indices says wavelengths toward the load or toward the generator, and it's useful for calculating the impedance along a transmission line. So for a number of years when we were doing the extra class, this is where we would stop, but I don't want to stop just yet, because I want to give you the rest of the story just briefly. So we talked about series impedance, series components, R plus JX, R minus JX, but there was also the parallel admittance. Remember, we looked at their equivalence with the parallel circuits. We're going to talk about the parallel universe. You get admittance curves by just rotating the Smith chart by 180 degrees. And you can take a look at this in more detail when you get home. So the unit of conductance used to be called the mho. I love that because it's ohm spelled backwards. But then they changed it to call it the Siemens, named after this guy, Werner von Siemens, in 1971. If you want to find more information about the Smith chart in a video, here's a URL for you. But here is a Smith chart that has both admittance and the impedance lines. And you use this to convert impedances from one impedance to another, and you do this in order for impedance matching. I'm just really going through this real fast because we're going to be running out of time, but L-network matching, the series element is described in the impedance Smith chart, the parallel element is described in the admittance Smith chart, and the goal is to cancel the load's reactance and to transform our resistance to 50 ohms. That's the whole point of it all. So just know about this. You don't have to know any details about it, but by combining series and parallel into an L network here, the Smith chart can be useful to calculate what values you need there, because the biggest reason for the Smith chart is impedance matching. Now, an interesting phenomena is voltage standing waves. We've looked at this before, and at this point, this is a high voltage point. Here's another high voltage point, and if you were actually to take a fluorescent bulb and walk it along a transmission line, you could actually get the bulb to light up at the high voltage points. We used to actually do this in VOA, and it was a quick check to see if you had impedances matched properly. But by adding a stub, you can get that high voltage point to go away, and the Smith chart can help you out in finding out where to put that stub. All right. More PDF handouts will be available to you tomorrow. There are some great videos from W2AEW here as well. And there's also software. It's called SimNec. It used to be called SimSmith, but now SimNec. Here's some URLs. You can use your computer to do these in simulations. And there's some great training videos from Larry Benko as well. All right. That is the end of your induction. Let's answer some questions and take a break. We have one more section, but it's really quick. So which of the following is an advantage of using an antenna analyzer compared to an SWR bridge?
Bravo.
Yeah, antenna analyzers compute SWR and impedance automatically. Which of the following is used to measure SWR? Read carefully.
Delta.
Delta.
Yeah, all of those can be used: a directional watt meter, a vector network analyzer, or an antenna analyzer. Which of the following can be measured with an antenna analyzer?
Charlie.
Bravo.
Charlie is true. Bravo is true. Alpha is true. All of those: velocity factor, cable length, resonant frequency. And which S parameter is equivalent to forward gain?
Charlie.
It's a two-port measurement, yep, S21. And which S parameter represents input port return loss or reflection coefficient?
Alpha.
Yes, S11, that's a single port measurement, yep. And what three test loads are used to calibrate an RF vector network analyzer?
Charlie.
Bravo.
Oh, no, Bravo. Bravo.
Yeah, bravo. Short circuit, open circuit, and 50 ohms. And how much power is being absorbed by the load when a directional power meter connected between a transmitter and terminating load reads 100 watts forward and 25 watts reflected? What do you think?
Delta.
Yeah, 75 watts is being absorbed. And what do the subscripts of S parameters represent?
Alpha.
It's the port or ports at which measurements are being made. And which of the following can be measured by a two-port vector network analyzer?
Delta.
Not delta.
Bravo.
You saw me do it there with that notch filter. You can measure filter frequency response. And which of the following can be measured with a vector network analyzer?
Delta.
Input impedance of a device, output impedance of a device, and reflection coefficient. Yes, all of those. And which of these transmission line impedances would be suitable for constructing a quarter wave Q section, that's a quarter wavelength matching transformer, for matching 100 ohms to 50 ohms?
Charlie.
You want to be midway between the two, so 75 ohms. And what parameter describes the interaction of a load and transmission line?
Bravo.
Reflection coefficient, it's what the big boys talk about, or return loss. And what is the velocity factor of a transmission line?
Charlie.
No,
Oh. Delta.
it is delta. It's the velocity of
Delta.
a wave in the transmission line, how fast it's going, divided by full speed, the velocity of light in a vacuum.
Delta.
Always going to be less than 1. 1 or less than 1. So which of the following has the biggest effect on the velocity factor of a transmission line?
Charlie.
Yeah, it's the insulating dielectric material. And why is the electrical length of a coaxial cable longer than its physical length?
Delta.
Yeah, electromagnetic waves move more slowly in a coaxial cable than in air. So what impedance does a half wavelength transmission line present to an RF generator when the line is shorted at the far end? So it's a half wavelength long and it's shorted at the far end.
Bravo.
Exactly, because remember, a half wavelength transmission line is an impedance repeater, so very low impedance. Half wavelength line, repeatance repeater. All right, and what is the approximate physical length of an air-insulated parallel conductor transmission line that is electrically a half wavelength long at 14.10 megahertz?
Charlie.
Charlie.
So we know it's a 20-meter band, and a half wavelength there would be 10 meters, and so the closest one to 10 meters is C, 10.6. But you can go through the math as well. So how does parallel conductor transmission line compared to coaxial cable with a plastic dielectric?
Alpha.
Charlie.
I mentioned it just briefly, and somebody got it there, alpha. That parallel conductor transmission line has much lower loss at any particular frequency than coaxial cable does, which is why it's good for really long runs. It's also why VOA used to use it, because we had really long runs from the transmitter hall. So which of the following is a significant difference between foam dielectric coax and solid dielectric coax, assuming all other parameters are the same?
Delta.
Do we see that?
All of them are.
Foam dielectric cable has lower safe maximum operating voltage, yep. Foam dielectric coaxial cable has a lower loss per unit, yep. Foam dielectric coax cable has a higher velocity factor, yes, all of those choices. And what impedance does a quarter wavelength transmission line present to an RF generator when the line is shorted at the far end?
Alpha.
Indeed, it's a very high impedance. If it's shorted at the far end of a quarter wavelength line, that's an impedance inverter, so it becomes very high. And what impedance does an eighth wavelength transmission line present to an RF generator when the line is shorted at the far end?
Alpha.
Not alpha.
No.
Charlie. Charlie.
It's an inductance. It's when it's shorted. All right. And what impedance does an eighth wavelength transmission line present to an RF generator when it's open at the far end?
Alpha. Charlie.
Charlie. Charlie. Yeah. It was inductor before, capacitor when it's open. Okay, good. And what impedance does a quarter wavelength transmission line present to an RF generator when the line is open at the far end?
Charlie.
Well, it's open at the far end. That's a very high impedance at the far end. And if a quarter wavelength line is an inverter,
It's going to be delta. Very low.
it's going to be very low. Exactly.
Open.
And which of the following can be calculated using a Smith chart?
Alpha.
Yeah, the impedance along transmission lines. And what type of coordinate system is used in a Smith chart?
Bravo.
Bravo.
Resistance circles and reactance arcs. And which of the following is often determined using a Smith chart?
Charlie.
Charlie.
Impedance and SWR values in transmission lines. And what are the two families of circles and arcs that make up a Smith chart?
Charlie. Charlie.
Resistance circles and reactance arcs. It's another way of asking the same question that we had before. All right, this is a Smith chart, but it's kind of turned 90 degrees. So on the Smith chart, what is the name for the large outer circle on which the reactance arcs terminate?
Alpha.
No.
No.
Bravo.
So where the reactance arcs terminate is the reactance axis. Here is the axis. I wish they hadn't turned this 90 degrees, but this is where the y-axis got bent around. That's the reactance axis. All right, on the Smith chart, what is the only straight line shown?
Delta.
The hint is it's the other axis. It's the resistance axis. So we have the reactance axis is the outer circle, and the resistance axis is the straight line. And how is a Smith chart normalized?
Charlie.
You reassign that number 1 to be 50 ohms, and then you use that all around the chart. So you reassign the prime center's impedance value. And what third family of circles is often added to a Smith chart during the process of designing impedance matching networks?
Alpha.
Constant standing wave ratio circles. A lot of antenna analyzers will show that as well. So what do the arcs on a Smith chart represent?
Alpha.
Delta, points with constant reactance arcs. And in what units are the wavelength scales on a Smith chart calibrated?
Bravo.
In fractions of transmission line electrical wavelength. Ladies and gentlemen, you made it through probably the hardest chapter in the extra class, I think. So go ahead and take 5 minutes, please. Relax. We've got one more section, but it's really short, and we'll get you out of here early. All right, 5 minutes. See you in a bit. And we're back. Thank you so much for hanging in there. A lot of stuff that kind of would make your head explode with the Smith chart and all, but the whole point of the extra class test is just to get you familiar with it, to know about it. Will you actually ever use one in your career? Maybe on an antenna analyzer display, you'll see a Smith chart display and you go, that's what that means. The SWR circles are kind of handy if you're making adjustments to bring a swept VSWR within the circles. That's handy. But probably not so much, but to pass the test, you need to know some of those basics. All right, the next section is one that I wish I knew a lot more about, and I've been trying to get the folks at our local ham radio club to have somebody give us a presentation on it so that they can be the expert, and that has to do with antenna design. So this is the last section, nowhere near as difficult as the previous one. So with computer antenna modeling, the goal is to predict an antenna's performance before you build it. You can try different options and see what happens on the computer. Well, that's great. I'd like to do that. And the software, there are two primary software is being used by amateur radio operators for antenna modeling. Of course, there's commercial stuff as well. But the software is based on something called the Numerical Electromagnetics Code. There are various versions of it. And the amateur radio software that's considered to be probably the best is EasyNEC by a ham, W7EL. It uses something called methods of moments analysis. And that's where uniform currents in an individual antenna or wire segments are modeled. It assumes that if you got, for example, a dipole antenna, it looks at segments of the antenna, and it assumes the current through each of those segments is the same. That's method of moments. And it used to be that EasyNEC was a commercial product, but he retired, Mr. Llewellyn, and so he made it available to hams for free. So you can go to this URL and download his last version of EasyNEC, version 7. And if you figure out how to use it, let me know. I want you to comment and we'll do a video and you can teach people how to use it. Because it's something that I stumble with. So EasyNEC, great antenna modeling software. Another out there that's also free is something called Monogal. Monogal was a joint production of some Japanese and German amateur radio operators. You can go to the URL here and download that as well. If you watch the DX Commander's channel on YouTube, he uses Monogal on his explanations of antenna modeling. And it's great to be able to do this on the computer and have an idea of how the antenna is going to perform before you do it. And remember, method of moments, or I like to call it MOM, is how these are based. And here's the technical details, but you don't have to know all of that. The main point is that the antenna is modeled in segments, each having a uniform current value. Or I think Dave Kassler said that every point along an antenna is treated as an isotropic radiator, and it's how they all form together to show you about the antenna's gain and pattern, etc. So some software quirks in both programs that if you go outside of your modeled frequency range, the antenna gain is not going to be the same, and that's kind of obvious. But then using less than the recommended of 10 segments modeled per half wavelength can give you the wrong feed point impedance. So for every half wavelength, you really have to have at least 10 segments. So what can antenna modeling give you? Well, it can give you standing wave ratio plots versus frequency. It can give you polar plots of far field elevation and azimuth patterns, and it can give you estimated antenna gain and front to back ratio. Now, interestingly, you can play with all these various parameters in the computer. If you optimize for maximum gain, which you think that's what I want from my antenna, you lose front to back ratio. So there's a trade-off, a compromise, a balancing act that you have to do between the various factors as you're building the antenna to find the optimum result. All right. Here we are to questions already. So what type of analysis is commonly used for modeling antennas?
Bravo.
Think of MOM, method of moments. And what is the principle of a method of moments analysis?
Alpha.
Yeah, wire is modeled in a series of segments, each having a uniform value of current. And what is the disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength?
Charlie.
Charlie.
Yeah, the computed feed point impedance may not be correct. And that, ladies and gentlemen, is the end of Chapter 9. You made it. I'm so proud of you. We have some extra time. Are there any questions or comments before we go tonight?
If I may go back, one of the very first slides you showed was a British one on a radio system,
Yes.
and far right, it highlighted in yellow was something about grounding.
And I told you to,
Okay.
we'll talk about grounding in the safety chapter. So don't obsess about that. Number one, it was written for the British standard, not the American. And in the American standard, the National Electrical Code, it says that all grounds must be bonded together. But those are electrical safety grounds. They're not supplemental grounds like for RF. So we'll talk more about it in Chapter 11.
Thank you, because I'm not sure I understand the difference.
Okay, and that's good. We'll talk about it. Any other questions or comments? Next week, Dave, what's
Right.
up?
Yep, next week will be Chapter 10. We're going to cover the whole chapter in one evening. It's about propagation. I think it's called Topics in Radio Propagation. We covered propagation as a broad subject area in the general class, so if you want general principles of propagation, I'd recommend going back and watching that chapter in the general presentation. This is going to get more specific about some niche modes of propagation, like rain scatter. You can bounce microwave signals off of raindrops. Some really exotic things there. So that'll be next week. So read Chapter 10, and I'll be sending an email with the Kastler links.
Thank you.
Very good, y'all. Thank you for your kind attention tonight. Till next week. 73, y'all. Get on the bands. CQ Worldwide CW contest this weekend. Enjoy.